Hey there, and welcome to Animation Square. As you can tell by the length of this video, we'll be digging deep into space, so put on your thinking cap and let's get into this. A black hole is a region of space having a gravitational field that is so intense that not even radiation or light can escape. The reason a black hole has such gravity is because of matter from a star after collapsing into itself has been squeezed in a very tiny space. Black holes are invisible because no light can escape. We can tell that black holes exist from special tools that observe a difference of how stars act when they are close to black holes. Black holes can be very large, but also could be as small as an atom based off of firm belief. Very large black holes are called supermassives that could be more than 1,000,000 times the mass of our sun. Scientists have proven that there is a supermassive in the center of every large galaxy. Scientists think that the smallest black holes were formed when the universe began, and scientists think that supermassive black holes formed with their galaxies. When black holes and stars are close together, they create high energy light. Humans can't see this, but satellites do. In fact, if a black hole were to replace the sun, Earth wouldn't be sucked in. Instead, it'd just orbit it. The black hole would have the same gravity, and the sun is too small to become a black hole. The theory of general relativity predicts that sufficiently compact mass could deform space-time and create a black hole. The boundary of the region where there's no escape is called the event horizon. Even though the event horizon has a giant effect on the fate and the circumstances of an object crossing it, according to relativity, it doesn't have locally detected features. Quantum field theory in curved space-time predicts the event horizons emits Hawking radiation with the same spectrum as a black body, of a temperature inversely proportional to its mass. Its temperature is on an order of 1/1000,000th of a Kelvin for black holes of stellar mass, making it impossible to observe. Objects with gravitational fields that are too strong for light to escape were actually first considered in the 18th century by John Mitchell and Pierre Simon Laplace on February of 2016. The LIGO science collaboration and the Virgil collaboration announced the first direct detection of gravitational waves, which also represented the first observation of a black hole merger. The no-hair conjecture postulates that once a black hole achieves a stable condition for their formation, a black hole only has three physical properties: mass, charge, and angular momentum. The most simple static black holes have mass but no electric charge or angular momentum. At the center of a black hole described by general relativity may lie a gravitational regularity, a region where space-time curvature becomes infinite. If you were to fall in a black hole, you would accelerate from the event horizon until you get to the singularity, and your body would be crushed to infinite density, and your mass will be added to the black hole. But before this happens, you'll be torn apart by growing tidal forces. The photon sphere of a black hole is a spherical boundary of zero thickness, in which photons that move on tangents to the sphere would be trapped in a circular orbit around the black hole. For non-rotating black holes, the photon sphere has a radius 1.5 times the Schwarzschild radius. Their orbits would be dynamically unstable. Hence, any small perturbation, such as particles of infalling matter, would cause an instability that would grow over time, either send the photon on an outward trajectory, causing it to escape the black hole, or on an inward spiral where it would eventually cross the event horizon. Rotating black holes are surrounded by a region of space-time that is impossible to stand still, called the Ergosphere. This is a result of a process known as frame dragging. General relativity predicts that any rotating mass would tend to slightly drag along the space-time immediately surrounding any object near the rotating mass would tend to start moving in the direction of the rotation. This effect is so strong near the event horizon that an object would have to move faster than the speed of light in the opposite direction just to stand still. The ergosphere of a black hole has a volume whose inner boundary is a black hole's event horizon, and an outer boundary called the ergosurface, which coincides with the event horizon at the poles but noticeably wider at the equator. Objects in radiation can escape normally from the ergosphere through the Penrose process. Objects can emerge from the ergosphere with more energy than they entered. The energy is taken from the rotational energy of the black hole, causing the latter to slow. A variation of Penrose process in the presence of strong magnetic fields. The Blandford process is considered a likely mechanism for the enormous luminosity and relative jets of Corsair and other galactic nuclei. By nature, black holes don't emit any electromagnetic radiation other than the hypothetical Hawking radiation. So astrophysicists searching for black holes must generally rely on indirect observation. This has been Animation Square. See ya.